Pablo, where are you?
Huh. I'm on holidays in Colombia, a place
No.
called La Macarena,
Oh,
uh, which has some rivers with aquatic plant that is kind of pink.
oh,
It's quite beautiful.
wow.
The place is called Caños Cristales.
Caños? What does it mean?
Caños means like mm, cascades, like a small river.
Uh-huh. Hmm. Looks warm where you are. Enough. Is it warm?
It is warm, yeah. And it's a lot of walking, seeing the nature. But yeah, I kind of badly planned the time of the talk.
Well, okay, I guess we can start.
Yep.
So we are recording and we are live on YouTube. Hello, everyone. Welcome to another KISS virtual seminar. Today, we will hear Pablo Arrighi talking about the complete story of a toy universe, how he solves the arrow of time problem in a mind-bending way in a toy universe. Pablo, the stage is yours.
All right. Thank you for the introduction and the invitation. This is joint work with Gilles Dewec. Gilles Dewec was my main co-author, and unfortunately, he died in July. He used to write a lot for popular science and promoted computer science teaching in high school in France, across the whole of France. Quite a famous figure for us. This is also joint work with Amelia Durbeck, who is quite alive and here. Probably she joined us and she will be able to answer questions as well when time comes. All right. So I want to talk first of all about the arrow of time problem, explain the paradox again and the current resolution, then bring some betterments, some solutions to the actual resolution, and then move on to a more perhaps crazy story about what our toy model says about, yeah, the beginnings. All right. So first of all, the the time arrow problem. So the time arrow problem is about distinguishing past versus future. Okay. So for us in everyday life, the difference between past and future is quite obvious. I mean, we are clear about the fact that we can go towards the future, but not come back. And perhaps we have an intuition why. And it's the old intuition that if I break a glass, it's going to be very hard to form it back. And so that could be the intuition that, well, if I have a video, YouTube video, let's say I have two buttons, a button that's play and a button that's reverse play, and I'm kind of not unsure about which button to press to see the video in the right direction. Well, the thing is, if I press play and I observe tons of explosions, uh, things that just break apart, disorder being created, then it means I've pressed the right button. That's the sort of rough intuition. But why is it paradoxical? Why do we have a problem here? Well, on the other hand, if we actually look in detail at the laws of physics, we know that at the microscopic level, things are totally reversible. So if I have a bunch of particles here, I press play, and then they move apart like this according to their velocity vector, right? This particle was about to move that way, and now it moved. Okay, so I observed loads of explosions, yes, but now if each of these particles, I I grab it, I flip the momentum vector, and now I press play again with the same rules of physics, then the particles that were moving apart, they will get back together. And if I flip the momentum vector again, then I'm really back to where I was before. All right. So the laws of physics, they are totally reversible. And in fact, they are even time symmetric, meaning that the laws you use to go back in time are in fact the same as the ones you use to um, move forward in time. You can observe that in the laws by just substituting a t by a minus t and find that the law won't even change, right? So basically, physics is kind of agnostic about past versus future, but we observe it in our daily life. And so this sounds like a kind of failure of physics to explain the most basic thing that we experience. Okay, so this is an old problem, and Boltzmann in 1896 had already come with a certain resolution, which is about precisely giving a quantitative, uh, if you like, um, well, it's about quantifying this intuition that we had, which is that moving towards the future is moving towards more explosions, more disorder. And here is how it goes. He defines the entropy of a state. All right, so what is this state? This is say, a glass of water. And right now we've dropped some wine at the top left corner. And so we kind of know that there is some wine here, and that the wine will dilute. Okay, so this does look like some explosion is happening, or in some sense. All right, but here is how Boltzmann will quantify it. At the macro level, we see that the wine is on the top left corner. How many ways are there to implement this at the micro level? Well, maybe the particle of wine could be here, or there, or there, or there. We kind of don't know, but we know that in this sort of 4 by 4 glass of water, flat glass of water, um, well, there are 4 microstates that corresponds to this one macro state, right? And so the entropy is 4. Well, it's not quite 4, it's the logarithm of 4, but okay, you get the idea. And so as the wine dilutes, it's going to be found everywhere in the glass. And now there are many more possibilities for the molecule of wine to locate itself. In fact, there are here 16. And now we see that the entropy is, well, log of 16. And so the entropy has risen. Okay. So the definition of entropy is that given a macro state, we count the number of microstates that implement it. Okay, with log, fine. And then Boltzmann defines the future as the direction of increasing entropy. Much that, according to the second law of thermodynamics, entropy always raises. Rather, it is that the future is defined as the direction of time in which entropy raises. Okay, good. So this explanation is fantastic, but it has a few problems. And let me enumerate 3 problems that it has. So one problem is that, okay, I press play and I see entropy raising. That's fine. That's fine. However, I may wonder how come it was low in the past? Because if you think about it, a state of low entropy is always a very unlikely state. So for the Boltzmann explanation to hold, I need to be given as a resource to start with a universe of very low entropy so that we have the freedom to shake things around and disorder them and witness the arrow of time. Okay? That is, the Boltzmann explanation works if God prepares me the universe in this very special state where the wine is concentrated at the top left corner. What would be much more likely is that wine be already mixed up in the glass. But if wine is already mixed up in the glass, entropy is maximal to start with. And now, if I observe the curve of entropy, well, it just will remain maximal. And there will be no past, no future, nothing. So that's one problem. Yeah, where does this low initial entropy comes from? Okay. Another problem that the Boltzmann resolution has is that of recurrence. Okay, so uh, it's true that I press play and I see that um, entropy raises, but if I keep on waiting long enough, then what's going to happen is actually that entropy is going to lower again and so on. And so, yeah, kind of means that the future is flipping direction or something. It's sort of counterintuitive. Why is that? Well, think about the glass of wine again. Of course, my molecules will dilute. That's true. But if I observe things at the microscopic level, there's no reason why things aren't reversible. And after all, these molecules will kind of bounce off the glass and kind of concentrate themselves back again at the top left corner. I mean, this is actually a theorem, right? In classical mechanics, this is the Poincaré recurrence theorem that says that if you take any mechanical system of a finite, of a bounded volume, what happens sort of is that, yeah, you change from one configuration to another, but at some point you kind of run out of configurations, in which case you have to come back to the earlier configuration. You cannot shortcut it, otherwise this would not be injective, this would not be reversible. So yeah, so just loop between configurations. Okay. All right. And third problem with the Boltzmann explanation. Well, okay, let's say I mistakenly I don't press play, I press reverse play on YouTube. And now what? Now entropy also raises towards the past. Let me just go back to the glass of water. Let's say that instead of pressing play so that this particle, bam, it hops right as it wanted, and this one hops down. Instead, I press reverse play. So this guy wants to come back, and this guy wants to come back, and now they bounce off, and start, they start running backwards like this. All right. Well, the point is the wine will dilute too. Okay. So there's kind of this saddle point. Where was it? Here. There is this sort of saddle point where if you go that way, then okay, future is that way. But if you go left, then future is going to be left as well. And that's just, you know, a problem that's already present in the Boltzmann explanation. Okay. All right. So now I want to tell you how to fix two of these problems. Of course, I mean, this is going to be a very simplified toyish model. I'm going to tell you about a universe that's one-dimensional. So we have one space dimension. It's periodic boundary conditions. So we are living in a circle, basically. And it's got two types of particles. It's got two types of particles. There's the left-moving particles. They hop left. And there's the right-moving particles. The right-moving particles, they don't move. They just move relative to the left movers. They don't hop right. It's just that relative to the left movers, they are hopping right, if you want. Okay. And now the rules of my universe are going to be that, well, we're going to, well, this is one step of time, okay? This f function is one step of time. And the rule is going to be that one step of time decomposes as up the left movers move. So for instance, this particle wanted to move, well, it moved, okay? This particle wanted to move, tack, where it moves, yeah, okay? And then there is some kind of interaction. And the interaction is flipping those patterns here. So if you find that two particles are facing each other across a link, like that. No, sorry, here. They are not facing each other. One is looking the opposite way as the other. This pattern here. If you see this pattern, then you're going to shrink the graph. You're going to reduce the graph in size. Two nodes will become one. They will merge, and the two particles will land on the same node that way. And the other rule is, well, it's an involution, really. So we are just really flipping these two patterns of the graph. And all this is happening synchronously, right? So I move my particles, and then I look for these patterns, and I apply this rewrite rule here. So this is a toy model I want to consider. It's quite inspired from the Haslacher-Meyer model of 98. It's some variation so that things become provable. The thing that I really want you to observe at this stage is that everything here is completely reversible. And if I want to make a quantum model out of this, it's a piece of cake, right? I mean, and this whole thing is a permutation over circular graphs. So I can really upgrade this to a unitary evolution without a problem. This is fully reversible, and it has this, well, this slight GR flavor in the sense that geometry is dynamical. Okay, of course, not at all implementing any Einstein field equation of some sort, but it's a dynamical geometry toyish universe. All right. Okay. So now let me study this and let me iterate. Okay, so here I got an initial configuration. I'm going to move my particles. So this guy goes here, this guy goes here. Okay, and now I see that there is this pattern that's going to merge. So now you see my graph is here is a bit smaller than this one. But then, well, this guy is going to move here, and this guy is going to move here. And now I see another pattern. This one is going to expand. This one's going to merge, and so on, right? And so now I've got 1, 2, 3, 4, 5 nodes, whereas here I had 6 nodes. So you see my graph has shrunk a bit. And one question I may ask myself is what happens to the graphs typically? Do they tend to grow in size, or do they tend to shrink, or follow a periodic have a periodic size? Okay. Turns out and this is the theorem that we've proven, it turns out that in this model, any graph configuration that's non-trivial, I mean, any graph configuration that has at least one left mover and one right mover will eventually grow in size like this. This is the theorem. You see, it's kind of counterintuitive because if I go back to my rules, there seems to be just as many reasons for my graph to grow as there are for my graph to shrink. But it turns out that in spite of this balanced appearance, no, just grab any graph. I don't know where you will be on this curve, but the point is the graph will grow. Let me give you a first intuition of why this could happen. I see there is a question. Should I take the question or
It's your decision. Do you want to have questions during the talk or only after?
maybe maybe some small efficient questions?
Is it a small,
Yeah.
efficient question, Deepak?
Yes, it is. It is. It's very small and very efficient. Hi, Pablo. Uh,
Hello?
so, no, I'm just not clear on what the graph is that you're referring to and how it's growing or shrinking, because everything is on a one-dimensional circle, and it seems like there's a finite number of degrees of freedom. So, in what sense is this graph growing or shrinking?
Yeah, so the graph is indeed just a circle. So it's a one-dimensional discrete universe, if you like. Each node can only hold, well, it can be empty, it can hold one left mover or one right mover or both of them. But what can change is the number of nodes in the graph. So the circle can grow in just the number of nodes. Okay,
Ah, I
according to these rewrite rules here. This rewrite rule is telling you one node becomes two.
No, but aren't you effectively introducing degrees of freedom by doing this?
Yeah, you could say that. I'm introducing degrees of freedom or I'm killing some degrees of freedom. But the
Okay,
point
you're
is,
not.
this is all reversible.
Right, right, right. Okay, got
In
it.
the
Yeah.
in the world of circular graphs of any size, this is a bijection.
Right, right, right. Okay. Okay, I mean, I have more questions, but I'll stop for now because,
Okay. All right. Okay. So these things always grow. And let me give you some intuition how this can be. So, for instance, let's consider this problem for a minute. Uh, Let me try and challenge you to find a function f, big F, which is a bijection from the natural numbers to the natural numbers. So something totally reversible that I'm going to be iterating. Okay. And I am looking for a bijection so that doesn't matter which number I'm starting from. If I iterate long enough, if I iterate t times which is higher than n, okay, if I iterate long enough, then for sure I'm going to be increasing my number. This t to f of t is going to be increasing. It's kind of, I mean, these things are kind of easy to construct, in fact. So if I go, if I take, if I divide even numbers until I reach zero, and then I bounce off the zero, and I say, okay, well, now I'm just going to increase by, sorry, I mean, I do -2 on even numbers, and when I reach zero, I do +1, and then I do +2, +2, +2, okay? You see that this is a bijection from the natural numbers to the natural numbers, but doesn't matter where I start. Let's say I start at 6. At some point, I'm going to be increasing, okay? And this is more or less what's happening with the size of these universes, these toy universes. Okay, let me give you a better explanation now that's like really related to the model. So a little proof outline. What happens in this model is that in order to shrink, you need to have this pattern, right? These two particles that are sort of moving away from one another, but just separated by a link. This is the pattern that shrinks. Okay. But you see that in order to shrink this pattern, I need to have two particles that the left mover is going to move apart, and then I'm going to find this pattern, right? So basically, the sources of shrinking of that little universe are those patterns here. It's the, let's say those little baby toyish black holes that are just absorbing matter around them. Okay. And these guys, turns out that they are very fragile. If I just throw a particle at them, and I just follow the rules, so now the left mover goes that way, and now I see a pattern that's going to expand instead of shrinking, and that's it. I've destroyed my little baby pattern, baby absorbing pattern. Okay. So then you can make your proof based on that. You can say, whatever the number of shrinking patterns, of merge patterns, turns out they will all be destroyed like this, and they will all vanish, and then things will only grow. Okay. So the point is, in this baby universe, the size of the universe is U-shaped. It's U-shaped. And since the size of the universe is U-shaped, the entropy of the universe is also U-shaped. That's kind of easy to prove because, well, first of all, you should notice that all the rules I've used, they preserve the number of particles, right? I mean, here I have three particles, three particles, three particles. I'm not killing or destroying any particles, just killing or destroying space rather than particles. Okay. And so let's say I have a small universe like this, like two nodes and one particle. Well, the particle can be a left mover on the left, a right mover on the left. Okay. There's four ways of placing this unique particle. And so this is going to have entropy log of 4. Whereas if the universe is larger, well, now there are more ways of placing my unique particle. Here there are 8. And so entropy is bigger. So yeah, so all I'm saying is as the universe gets bigger, there are more ways of placing the same amount of particles. So of course, entropy is going to grow, right? Okay. So that's it. We've got this smallish toy model where entropy is definitely U-shaped. Okay. So this is kind of solving the problem of how come entropy was low in the past. Okay. Boltzmann needed this God-given resource state plus the laws of physics in order to be able to demonstrate an arrow of time. Here, we don't need that God-given state. All we're saying is, no, any configuration, give me just any initial configuration for the universe, size of the universe is going to be U-shaped, and entropy is going to be U-shaped. So entropy is going to grow. Okay. If you like, it's then Big Bang happens, and now we're out of equilibrium, and now things will disorder again. This idea is quite is quite common about cosmologists, and it's been argued several times before. But this mechanism of a piston compressing, and then you release the piston, and then you witness the arrow of time. The problem with this is who's pulling the piston, right? And is the mechanism of pushing and pulling the piston itself reversible? Because if your explanation relies on some irreversible mechanism of pulling and pushing the piston, then you've sort of failed at the rules of the game. The rules of the game was to have something completely reversible and yet witness the arrow of time, right? So what our model has is a mechanism, if you like, for pushing and pulling the piston that is itself completely reversible and local. Okay. The other problem was the problem of recurrence, the thing that the Poincare recurrence theorem, the fact of being periodic. Well, here, clearly things aren't periodic. They are U-shaped. And so we won't have the future flipping back to the past or anything like that. And the fundamental reason for this is that the size of our graphs is unbounded. We are talking about a finite size universe, but a finiteness that can grow and can be arbitrarily large, right? This is why we escape the recurrence theorem. Okay? And the last of the three problems was the Janus time problem. The Janus time problem is this thing about the saddle point, right? So here too, I mean, let's imagine that we are right now 13.7 billion years after the Big Bang, and we go back to the Big Bang. And let's say we go back even further, and we go at 27.4 billion years ago. And according to this explanation, these people in our faraway past, they would be observing the universe expanding that way in the reverse play direction. And so they would see entropy as going that way. And so they would be experienced future as going that way. All right. And here we see a very important difference that we have to keep in mind for the last 5 minutes of the talk. There is a difference here between pressing play or reverse play, that is running my physics laws in one direction or another, applying F or applying F minus 1. This is dynamical time. And here I observe it in the horizontal axis. And there is another time here that is being shown in this picture, which is whether entropy is raising. And entropy is raising that way, and it's raising that way. So this is the entropic time, right? So, and that's kind of showing in the vertical axis here. Okay, so that's kind of crazy, this notion of a Janus time that has been argued quite a lot by Julian Barber from Oxford. The Janus is this picture of the twins, right? One twin facing another, because one sees time in one direction and the other one sees time going in the other direction. Okay, but I want to say that after all, let's indulge for 5 minutes into taking these things seriously and exploring the consequences. This is kind of fascinating, and it gave rise actually to
Pablo,
yes?
you have around 10 more minutes.
All right, but okay, I may not need them. Thanks. So we got this popular science paper about this. So what I want to do is answer a kid's question. Because when we were kids, we used to ask a lot of annoying questions to our parents. All right, we used to ask the question of, well, where does time come from? When was the beginning of times? I used to ask this. And here you have two kinds of possible answers in this setting, right? You can say, look, what are you talking about? Are you talking about entropic time or are you talking about dynamical time? If, my child, you are talking about entropic time, then entropic time does have a beginning, right? It does have a minimum. If I go back to this picture, there is a minimal entropic time. So there is a beginning, but it's kind of frustrating because you don't understand really where this entropic time comes from. And it's only until you sort of unfold, you just picture the U and you just rotate the U like this, that you realize that, okay, well, maybe entropic time has a beginning, but its root cause is the underlying dynamical time. Okay. And so if now your question, my child, is does dynamical time has a beginning? Well, in this model, we can answer it hasn't. It's a B infinite line. It was always there. Okay. Now, let's go back to more childish questions. And let's say the kid now wants to know where matter comes from. Like, yeah, where does thing come from? I mean, the trees, the carbon, the hydrogen. And so my father would tell me, look, it comes from the Big Bang. Everything comes from the Big Bang. But then you're like, okay, but where does the Big Bang come from? And usually you don't get any more answers at this stage, right? Well, here in this toy model, it's clearly the case that we have a big bounce, right? At least I phrase things in dynamical time. I clearly see a large universe that shrinks to a very small size and then expands. So the dynamical time explanation to the kid is, look, there's been a big bounce, a big crunch, and then a big bang. All right. But then again, this explanation is kind of not very satisfactory, in my opinion, because everything we witness around us is expanding. Entropy is growing. We are believers of the Big Bang, fine, but Big Crunch. I mean, it's kind of very strange that an entire universe would collapse to being the size of the head of a needle, right? So here, instead, we would perhaps give a better explanation if we adopt the entropic time perspective. And we tell the kid, well, from an entropic time perspective, what's happened is a big double bang, meaning that we see a big bang and we experience expansion of the universe towards our future. But from that same point towards what seems to be our past, this kind of twin universe is experiencing a big bang too. Of course, for them, future goes that way. So there's this point of a big double bang. And where matters come from, well, our matter comes from the past of their matter and reciprocally. Okay, so it's a double birth, and one birth causes the other birth somehow. This seems very philosophical and a bit crazy. Nevertheless, you have to remember that this is about very, very simple rules. Yeah, those rules. And those are rules that we completely master, right? I mean, everything is there in this slide. You can put it in your computer. You can run it for 1 billion years one way and 1 billion years and the other way. Everything is there. You just have to read things. And what you read is this story that I just told you about. Okay. So, of course, it's the complete story, but it's the complete story of a very toyish universe. So let me just conclude the talk by saying that, here we have been looking for a physics explanation of the arrow of time of and origins of times and so on. Physics explanation meaning you get some law, you get some nice little laws to play with, and they induce the phenomenon. Of course, we're not trying to explain why would the laws be that way or another. Here, basically what we've been saying is that if you've got totally reversible rules that are capable of shrinking and expanding space, then you will find a difference between past and future. You will find this U-shaped curve that's basically giving you an entropic time for sure as you run your laws. We believe, okay, we've done this in a very toyish model, but actually we think that this explanation is very generic, and maybe Emilia will be able to tell you a few words about that, because recently she's been with Paco Perrotin enumerating rules like this and finding that, yeah, actually, generically, they are behaving like that. And so in the end, you end up having this explanation of dynamical time causation of the beginnings of entropic time. And you also end up having this idea that that you have this double birth in 2 directions, this double Big Bang kind of thing, the creation of our universe from a symmetric one. Yep, that's what I wanted to tell you about. And I'm open to questions.
Thank you very much, Pablo, for your talk. Let's click on the clapping hand gesture, which I cannot find. Oh, there it is. Yeah, please ask questions with raising your hand. Deepak, please.
Yeah. Hi, Pablo. So this is really amazing work because it's very simple and it tackles something very important. But there are a few questions I have and also a couple of comments. So if I take too long, Ofek can always shut me down. So the first thing is that if you have a reversible, if you have a possibility where the space can expand or be compressed, then are you not automatically providing a mechanism for entropy to increase indefinitely because you are increasing the number of possible configurations that the particles in the system can have?
Yeah, that's definitely the idea. Now, the thing that's a bit fragile about the arguments here is, yeah, you're providing a mechanism for things to expand, all right? But you're in a reversible world, right? So as you provide a mechanism for things to expand, you are also providing a mechanism for things to shrink. Sorry, I should have, yeah, to shrink. That's going to shrink, all right? And so when I introduce that rule, I'm not really sure what's going to happen. Am I going to actually reduce the size of the universe or enlarge it? And it turns out you enlarge it. Okay.
Mm-hmm.
And then, yeah, that's it. Then you're right. As things enlarge, then you've got more space to put the same number of particles, entropy grows.
Okay. So then I have just a few comments. The first is that this kind of evolution is exactly what arises in loop quantum cosmology, where you get a two-sided time evolution. Uh, that's the first thing. The second thing is that there's recently been work done by Neil Turok and Latham Boyle, I think, on something called a CPT symmetric universe, and they also have a similar picture, which comes from a different line of argument. And then the third comment is that there was some work done a few years ago by Barber and collaborators. I think Tim Kozlowski or Pawlowski, I forget. It was a PRL paper, I think, on again showing the emergence of a arrow of time in a system of gravitationally bound particles. Do you remember?
Okay,
Do you know about that? Or
so let me answer in turn. So this idea of using solutions of GR which are a big crunch in order to restore CPT symmetry is something that is actually dating back to Sakharov in the 80s, right? So there is a paper like that already. And the aim of his paper is really about CPT symmetries. And I wouldn't be able to tell you much more about that. Now, there is also another solution by Hartle and Hawking that is also giving you a big crunch. Um, so yeah, so the thing is, in those GR-based model, reversibility is not that clear, is not that manifest as in our model, right? Uh, the and also the Carroll chain, they are the first one to really discuss the arrow of time in the context of GR, and they are saying, look, if we had a GR kind of reversible way of expanding and shrinking the universe, then we may observe we may solve this question of this problem of the past entropy hypothesis, right? But then themselves ask, but okay, but is the GR expanding and shrinking mechanism really reversible, right? So if you like, the point here is to really establish clearly how it could be the case that shrinking and expanding a universe can be local and fully reversible. The cosmological loop quantum gravity model, I don't know much about. I would love to have the citation. And there's one last thing that you mentioned that I didn't answer, I think.
yeah,
Yeah.
that's the paper by Barber. You referenced a
Barber.
paper by
Okay, Barber. That's interesting. So that there are
yes.
great advocates here. I was citing it in the slides.
Mhm,
There are great advocates of this Janus time,
mhm.
and the model that they use is basically, let me just take the plane, Euclidean plane, and let me sprinkle a bunch of particles there, like 5 particles. And you will observe that these 5 particles, whatever you do, if they run straight, let them just run straight. Well, at some point, maybe they will cross each other or something, but then each particle is going to go their own way, right? And so if you take as your universe the, the sort of occupied area of the plane, then this occupied area of the plane is also following some kind of a U shape. Okay. So this is the sort of argument they are making. They're making, let's take a random universe by sprinkling 5 particles, and let's look at the shape, it's U-shaped, so something like that. We think that okay, it's a great analogy, but it's got some weaknesses too, because what would be more typical in an infinite 2D plane is not 5 particles. It would be like, for instance, a constant density of sprinkling of particles. And if you do that, then you're already in the maximal entropy state. So in our model, the key difference that there is in our model is that our model is finite but unbounded. Okay, the universe is a finite size, but still this size can evolve. And that's the sort of ingredient that is, in our opinion, missing in their work.
Mhm. Okay, I have another question, but I forget what it is, so I'll come back later. But yeah, thanks.
Um, I also have a question, Pablo. Do you know about Penrose's idea of the cycles of the universe, cycles of time, the epochs?
So I haven't studied it. I've heard of that. I think it's the idea that yeah, even if the universe may grow, some kind of a scale invariance or rescaling things will make it look as if it was small again with the same kind of densities, and then you will be able to restart the story, but at a different scale, right? That's more or less the idea.
Yeah, I mean, he does build on the idea that regardless of scale invariance or coordinate transformations, that when the entropy reaches maximum, there is some probability, like after long enough time, it will go down again and then will reach the low entropy of the Big Bang, like after gazillions of years. And yeah, now it is very similar, at least it looks similar to what you're talking about, except he's not talking about the Janus time. So you're saying that in the other side of the Big Bang, if something happens there, if you can take time backwards, then and we can take time backwards in the equations, and we expect that the entropy will also go if we take it backwards, that there will also be a universe there before our universe. Like there is no.
Well, I'm saying that in the toy model, this is what happens, definitely. And it seems likely. I don't know.
Mhm. Okay, but do you, so in the toy model or in the or in what you want to infer about the actual universe, do you see it that the universe begins, like our universe began when time goes on the play button from the zero, and on the reverse play button, does the other universe begin or does it end there?
It begins. In entropic time, it begins. And
Ah,
in dynamical time, it ends, right? I mean, let me try to. Yeah, the picture you have to have in mind is this. Like, if you look at dynamical time, then okay, it's ending, but really that's not the way they feel physics. They feel physics with respect to entropic time. So for them, it's physical time is really going that way. So for them, this is where it 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 gets born.
okay, so so as you said, our birth is their birth.
Yes.
Our end, what happens to this model when you begin with maximal entropy and not with minimal entropy? Does it go down at some point?
In this model, you cannot really, there is no maximal entropy in this model because you see, I can take a circle and I can sort of fill it with particles, but these particles, they will meet each other and they will expand the graph and so on, and the graph will grow bigger and there will be more sizes to place the particles. And so there is no such thing as maximal entropy.
I see. Now, do you expect that it will be different quantumly? Because this is a classical model. Now, I don't know, if there are some quantum effects or some
I
field
think
that.
this can be, I think the question of the arrow of time is not quantum. I mean, and to be honest, I owed really this thought to Carlo. I mean, Carlo has really been questioning us and putting us on the track of trying to find a solution to this past hypothesis question. And we are starting to look at it from the point of view of quantum mechanics, but he was saying, no, look, and it's here there is nothing quantum, but everything can go quantum easily. Just
Hmm.
think of this permutation as a unitary operator.
Sorry, can I intervene? I can answer also the fact that we tried to run that model with quantum variation of it. And the things that we were able to simulate, because it's a quantum system, so it was a nightmare to simulate, but the things that we were able to simulate showed the same behavior.
Okay.
But we couldn't do more than 13 steps, so it's hard to have a definite answer. And we don't have the proof but yeah.
But is there a reason to think a priori that it will be the same? Because maybe you are able to apply more rules, maybe splitting and combining are different in quantum. Maybe there are more options.
I mean, that's possible, but the experiments that we had didn't show that, and my intuition is that it's not the case, it behaves the same, but I mean, intuition for this type of system breaks really easily, so I'm not confident at all on that.
Mhm.
I mean, if you could imagine a quantum mechanism to try and prevent this to happen. So for instance, if you were going to put a phase on each link, then the more links you have, the more you have phases, the more you are at higher energy, the more you are hoping that there are some destructive interference effects, and then you try to kill off large universes by means of destructive interference, for instance. I don't know.
Hmm.
You could try and engineer stuff so that it doesn't happen. But
Hmm.
there's
So
a few
you
questions.
numerically. You only answered it numerically. You only got the U shape of the entropy numerically. Or did you get it also analytically?
In the reversible model, it's analytical, but if in the quantum one, it's just like what we observed.
Yeah.
Numerically, it was only numerical.
So the fact that it is independent on the initial state is a numerical or an analytic result?
Analytical results.
For this toy model, it's analytical. Here,
Yeah.
it's really a proof. Now, in general, we can explore much more complicated results numerically, and we find more complicated models numerically, and we find the same.
Mhm. Okay. Thank you for this answer. Ding Jia, please.
Hi, Pablo.
Hello.
I have a question/comment. I'm not sure you've given a satisfactory explanation for experiential error of time. You started to talk, raising a question about our experience. We look around ourselves, we see phenomena, and in our experience, we seem to feel that entropy increases.
Yes.
However, it seems you cannot address a question about experience without mentioning experience. In particular, in your model, you said nothing about what observers would experience. You just shown us that a model where entropy can keep on increasing without bound. But for example, more concretely, I'm imagining in your diagram of the U-shaped, yes, this diagram, I'm imagining I'm born, say, towards the right half of the picture. I'm currently living on the right half of the picture. And in your presentation, you would assume that my future will go towards the right.
Yes.
And if I'm born on the left half of the picture, you would assume that my experience goes towards the left. In this case, my entropy will grow. However, I don't see why the opposite case is ruled out. For example, if I'm born on the right, why
Yes.
can't my experience points towards the left? It seems you have to say something about the error of my experience to make that assertion. And I'm not sure I've seen that part.
Okay. So I think we've tried to to address this question in the paper, you will find that we not only look at the global entropy of the entire universe and see whether it's raising and so on. We also look at windows, like we look at a little piece of the graph of size 100, and we count the number of particles there, and we try and see whether our entropy is growing locally or not. Okay. But it's kind of a difficult question to address, I must say, because what happens is that as the graph grows in size, the number of particles, well, there are less and less, density drops. And so more and more, what you observe is that in your finite local window, you just see nothing, And in fact, entropy is really low locally because it's just empty space. Now, is that something that makes the model unrealistic? Not really, because this is also what's happening at the scale of our universe, right? I mean, our universe is expanding and it's running towards thermic death, right? I mean, there's less and less stuff happening, really. So yeah, so I'm not too sure how to address this question. I think it's a good question, but it's kind of hard to quantify.
Yeah, I guess maybe we just need to model observers explicitly in
Yeah.
cellular automata models or other models.
Oh, but sorry, I did at one point, and so basically, if you're an observer, you're limited by the speed of light, quote unquote, which is ours. In our model, would be the speed of the particles, and you would have local windows that grows linearly in that grow linearly. And if you run that, you basically have the same results that as the global entropy. Just you have to rescale by a factor, but it's the same story.
What I'm not sure is why my arrow, so suppose I'm right now on the right half of the picture, why my future doesn't point towards the left.
So it does if you so if you start with a typical universe, like you flip a coin basically of if you have a particle or not, you run you are already at the minimal entropy and you increase. But if you take an atypical state and you try to start in a untypical configuration, half of the time you are already in the right part of the universe and your entropy grows directly. Half of the time the entropy diminishes for some times. It's diminished for a time and then it regrows. So if you play the play button, it goes that way. It depends. You have 50-50% chance to go on one side or the other.
Which means my entropy has a 50% of chance of decreasing? Or?
Yeah.
I think if you start here and you press the play button, I mean, if you
Yeah.
start here and you press the reverse play button, no problem. Entropy is going to increase straight away. But if you start here and you press the play button, entropy is going to go down for a while, and then it's going to go up forever, right? So the period of time when it decreases is negligible compared to the period of time where it increases.
But it could be the period of time of decreasing entropy could be 13.7 billion years.
Yeah, but it's negligible.
Okay. I think I got
in a U, the bottom of the U is always negligible.
Well, okay. I think I got what you've gotten so far, and I'm happy with the answer.
Right.
Great. Thank you for the question. Lorenzo, please. Lorenzo? No. Okay. So who was first, Ognian or Deepak? I think Ognian. Okay. So Ognian, please.
Okay, I was not first, I think, but never mind. Thank you. I'm trying to understand something here because you mentioned this work of others that with the five particles example,
Yes.
and this is what I was thinking about when you started presenting your model. And similarly, for instance, even in quantum mechanics, you can just imagine a wave packet. It's a typical behavior. I think that it might shrink depending on its initial state, and then it's going to spread out forever.
Hmm.
So this behavior we kind of have, and I was wondering why I couldn't fully understand why you were unhappy with that type of observation, and in which way your solution is, which exact drawbacks does it overcome here? In the sense that if I see there is this maybe just to elaborate a little bit my thoughts here, you say that you address the Poincaré recurrence issue. And I was wondering, like, if I look at this, what you did in the space of all graphs, like you said, it's an infinite space.
Hmm.
Isn't it analogous this what is going on? You don't have recurrences because you're in this infinite space, like in these other
Exactly.
examples.
Yeah.
Huh. So, in which way
So
then is this?
regarding recurrence, you've got it. I mean, you're in this infinite space, so you can escape recurrence. Okay.
Mhm.
But on the other hand, if you take your typical infinite space, then it's very hard to define what would be a typical initial state. And now I'm back to this first problem, the problem of the the past hypothesis, right? So the past hypothesis problem is that in the Boltzmann resolution, God needs to give you a universe that is really well ordered so that you can disorder it. And that's kind of weird. So the question here is trying to do away with the need for a particular low entropy state to begin with, right? Now, if you take your typical infinite plane, for instance, as they do in the Barbour paper, what would you regard as a not special, a typical state? Okay. And like putting five particles, isn't that very special already? I mean, why five? Why not just sprinkle the whole space?
I assume my understanding of this argument is okay. Take any state, basically, just take any microstate. It's going to have this behavior. I think this is a kind of good. I would say maybe satisfying explanation as to why we would see it like forever certain quantity. I mean, this was my second question, has to do with the thermodynamic entropy, but like, for example, like the volume that it occupies or something like that will have this behavior. So it seems to me, I don't know, that the fact that you're making an observation that any state has this behavior, and then the actual state in which we find ourselves to live, not surprisingly, after some time, will be displaying this behavior. So you're happy with this explanation, I would say. Um, so maybe what I'm missing here is because you're suggesting that somehow this need for to refer to an assumption about the past where the entropy was lower. But this again is a bit tricky because here we're
Mm.
invoking the thermodynamic entropy. But still, just to understand, in the context of your model, how do you like in which way do you not need to assume an initial state, or is it not? I mean, you start from some state
So
in this
here,
infinite space.
any graph with at least a left moving particle and a right moving particle will have this U shape of size and of entropy. So it's not that I don't even need a typical state. I mean, just all states behave like that.
Uh, but I believe that's also the case with the other ones, no? Any number of particles in an infinite universe, of course, will have this behavior. It's
Yeah.
just because the infinite universe allows us to any finite system inside it in
Yeah,
this
that's
a
right.
priori space will have this behavior
I
somehow.
mean, there are,
Yeah.
I mean, again, I think the Barbour model is a great analogy. I'm not saying, but so first of all, you could argue that starting with a finite number of particles inside an infinite space is already a bit wrong. It's already really going towards a very atypical state. Don't you think so?
Not necessarily, but I wonder how is this not the
Mm.
case in
Well,
your
in our model, the universe is always of finite size. It's unbounded
but in the
in
space
size,
of in
but
the
the circle
space.
is of finite size.
So you're assuming if your measure of entropy is the number of like dots on the circle,
Hmm.
are you not assuming that you start from essentially from a low entropy, whatever, or not start from in a sense of like something in the past, but rather you're focusing on a specific microstate, so to say, and then you look at how it's gonna behave. But in the space of all the possible configurations, it's still a finite thing to begin with. You're focusing on one specific microstate in the space of all possible microstates, just like
I mean, I can start from any microstates in the whole space of microstates. So of course, in the end, I'm starting from a microstate, but still, any will do. Now, also, perhaps what you could argue is, mm, modeling the expansion of the universe by particles going apart from one another in a 2D plane is perhaps a bit frustrating because the 2D plane is what should be expanding, not the particles on them, right? So here in this model, we are taking one step closer to something that is more general relativistic, where it's actually space itself that is expanding.
Mhm. Okay, I don't know if I have time for my second question was more about specifically the link to the thermodynamic entropy. I was wondering about the analogy here because mm, is it how I understand the Boltzmann argument is like once you define the entropy, typically you focus on macroscopic observables, right? And then you define your thermodynamic entropy to be the number of microstates compatible with your macroscopic
Yes.
value. And then essentially you argue that you shouldn't be surprised that although the universe evolves reversibly, that we happen to be in an in a area in an era, let's say, of expanding entropy, provided that you make the past hypothesis. Okay, and now, but this thing here now you don't have the somehow. I was wondering this the to which extent there is no typicality argument in your it seems, or maybe it seems, but there's somehow that there's not a typicality argument in your analysis. And that is interesting because in the other argument, the Boltzmann argument, the definition of the entropy is concerned with this volume of possibilities, and then you just argue that the typical state will have the behavior we expect provided the initial condition. And here there was not quite the same somehow. And I wonder, is there an analogous argument that will link this to typicality somehow? Because the number of sides on your circle is your analog of the entropy, if I understand correctly. And this grows. It's not, I do not, I wonder if there is a more precise connection to the other notion of entropy. That is
Uh,
Boltzmann.
so one thing perhaps I should have said is that what plays the role of the volume is really the size of the universe.
Mhm.
And then, in the three variables are for a perfect gas, right? Volume, pressure, and temperature, right? We don't have temperature. Temperature would be linked to the speed of the particles, but our particles, they all go at light speed. So there is a kind of, this variable disappears. And then there is the pressure, and the pressure is the number of particles in the volume. So our entropy is really the analogous here of that of a perfect gas in this kind of toyish model. But yeah, just well, to address the question more specifically, no, I would say that we don't need typicality arguments here. Just things are simple enough that we don't need them.
Thank you.
Okay. Seems like there are no more questions. So thank you everyone who asked questions, and thank you Pablo and Amelia for answering them. Let's thank Pablo again and Amelia.
Okay, thanks a lot for your questions and your patience.
Very interesting work, Pablo. Thank you. Bye bye everyone.
Bye. Take
Bye.
care.